Alright, so hello and welcome. I turned the volume way up because I just want to whisper because I think it's kind of late. People are trying to sleep. But yeah, so we're going to take a look at another question. Pretty late today. I don't know. My mind's been all over the place lately. I don't really have a good excuse either. So there are actually two other problems I want to look at tonight, if I can. I want to look at UTF-8 validation again. And I also want to look at binary search tree validation. We'll do those two things. We'll come back to that in a moment. Given the root of a binary search tree, VST, or the values of exactly two nodes of the tree were swapped by mistake, recover the tree without changing its structure. Oh, this is very similar to what I was just going to do. I actually know what to do. 3 cannot be a left child of 1. It's 3 squared than 1, swapping 1 and 3 makes a BST valid. Example 2, 3 and 2. Well, this is very similar to what I was thinking about doing. Number of nodes in the trees in the range 2 in 1,000. Problem solution using linear space is pretty straightforward. Can you devise a constant time solution, constant space solution? Interesting. So they want us to actually swap the nodes. Yeah, without changing its structure. Interesting. I'm not really sure what's meant by not changing the structure. Like, in this case, you could take, we could do something like this. A little confused. Okay. So that is what they want us to do, is to actually just change the data inside the tree. I mean, that's fine, I guess. So, let's see if we can figure this out. Let's try to do this in a way that's, let's do just some solution that works at all, right? Not necessarily a good solution or an efficient solution, but just some solution. So one way of doing this is, it would be, I guess, first things first, you could try, like the worst solution would be 2, that would be roughly n factorial, but like n plus 1 factorial would be to try every permutation of the data in the nodes, and then after each permutation verify whether or not you're looking at a binary search tree. That would be too expensive though, because this has 1,000 nodes in the tree. That wouldn't use extra space though. That's one approach, not a very good approach, but one approach. The next idea would be, so these two nodes, they're not next to each other anyway. They're just in the tree somewhere, and they're swapped. So what's interesting is there would be some error. I want to say in logarithmic time you can find the first error. and then you should be able to find the second error. The error could be in the left subtree, it could be in the right subtree. You can write two subroutines, just find error, and find the first error. And I suppose, well, either the root node is, so I'm not sure exactly how you'd want to do this, but you could do something like, and maybe you can use a level or a traversal to do this, so you can maybe find two errors. Maybe that's the way to do it. So, you want to find errors. So the thing that's tricky is this node at the top is not an error, but the second node is, or this two node is. Like given this structure 1, 3, 4, actually there is a way to do this that's kind of interesting. If you perform an Inorder Traversal, and yeah, as soon as you if you perform an Inorder Traversal, then you can figure out that one of these values is not in the right spot. So there are a few ways to do this. Pretty straightforward. Linear time. You could, what you could do is dump all the values into an array, sort the array, and then rewrite all of the values back into the binary search tree. Something like that. I don't know if that's really straightforward. I wouldn't say it's straightforward at all. The problem with that is that, how do you read the values back into this binary search tree? I guess what you could do is, you could write the tree node pointers to an array, and then read off, right? So as you traverse, you build two arrays. You could build the tree node pointers array, as well as the data array, and then when you sort the data array, then you can write to each node in the tree node root array, index by index. So you could do something like the following. Okay. Let's see if this works. If we do this. Okay. So actually want to perform an Inorder Traversal. So an Inorder Traversal is you do the left side first, then you do the root node, then you do the right side. So an Inorder Traversal we can perform, and then we can say standard sort data begin data.end, and then we can say for we're gonna say tree node pointer p. Actually, I want to do more like this. We're gonna say tree node pointer of p is gonna be pointers, excuse me, of I, and then we're gonna say p value is equal to date of I, and then we can return root. Something like this, I believe, will do the trick. Oh, maybe, okay. That might be because it's const. That might be the issue. I think this will solve the problem. How do we do it on time? 11 minutes. Oh, yeah, I tend to forget that as well. I often forget that. Oh, excuse me. Yeah, we don't even, right. Forgot about that too. Yeah, so this is probably correct. I could be wrong about this though. I don't think so. I don't think it's possible to be wrong if taking this approach. Let's go for it. There could be something wrong. I don't know. I'd have to like test more stuff and spend the time. Oh, there we go. Okay, done. So that's what they're suggesting. A really simple approach. That took 12 minutes. That's pretty good. But the question is, and by the way, you could do the same thing using a depth first search. Or breadth first search rather. We should do this with a breadth first search. So because I spoke with, there was an interview a while back that was saying I should do iterative approaches, like breadth first search rather than depth first search. Do things iteratively. So we're gonna do that instead. We're gonna use a breadth first search. Which, by the way, we didn't include our vector here. We didn't include algorithm either. And we're going to also include a queue. So, actually, I don't know how we can, I take it back. I don't know if we can do an Inorder Traversal with a breadth first search. I take that back. That might not be possible. Can maybe do it like a deck kind of deal. Yeah, actually, you're better off using a stack, actually, at that point. Better off using a stack. Yeah, well, we can do it with a stack then. That's fine. Let's try that. Technically iterative instead of using the call stack. Let's try that. basically just do the same thing here. So, yeah, you can do a depth first search iteratively in theory. So we're going to say tree node R is going to be st dot top. So yeah, it's not empty, so we can put the top. If not R, then continue. Then st, and we could pop as well. Pop immediately. I believe so, right? We can. Actually, I'm not sure if we can do it this way. What you would do is it's more like a queue, actually. I'm not really sure now. I'm thinking about it. Can you do depth first search can you do an Inorder Traversal with just a stack? Is that possible? Well, you would push before you pop. Before you pop the how do you know? I want to say something like you push. I'm actually not sure if you could, how to do this. I don't think so. I actually don't think you can use a stack to do the Inorder Traversal. You could do the left subtree. And what would you do though? I don't think so, man. It's not as simple as just pushing the left side and then pushing the right side. Because you need to process what you just pushed onto the stack. Maybe you could do with a double-ended queue, something like that, like push on the left side of the queue, push on the right side of the queue. But what about something that's like a tree that has more than one child, like multiple children? Well, Inorder Traversal doesn't really make too much sense if it's not a binary tree, right? Because you're kind of just randomly selecting what order you're gonna walk through things at, or how you're gonna walk through things. There is such a thing as threaded binary trees, and there's an algorithm, I forgot what it's called now. There's iterative traversal of a threaded binary tree without recursion. That's what I'm looking at, what I'm looking for. There's a name for this algorithm though. I forget what it's called. Excuse me. What you can do if you wanted to is run an iterative traversal of the tree. And what would happen is, in two spots in the tree, left to right, it should be in sorted order. Except at some point you'll find two values where it's not in sorted order anymore. the question is 2 spots that'll happen. What's tricky about that is trying to figure out which of the 4 different combinations gives you the right sorting if you swap those values. I'm actually not sure. We can still do this without doing on Inorder Traversal recursively. I don't actually think you could do an Inorder Traversal with just a I don't think you do it with just a stack. I take that back. I think I'm wrong about that. There are a few things to say about this. I want to say there's another issue here, which is hi, hey, how's it going, Melito? Welcome back. Hello, hello. Howdy. How are things? How are you? Welcome, welcome. There's another issue here of there's another issue here where there's an algorithm to do this as well. It's got a name. There's a person that Morris. Yeah, I struggle to remember, but there's a Morris Inorder Traversal using threading. You can do a level order traversal, breadth first search, but that's not what we're looking for. You can also do breadth first search using iterative deepening, breadth depth first search, which is more space efficient. Which I forget exactly. Yeah, iterative deepening depth first search. The space complexity is a lot less, right? Right, of the depth. Whereas, yeah, so you can use iterative deepening to do a depth first search or breadth first search. It's a breadth first search, but it uses a lot fewer nodes. This is a very interesting approach. A lot less space. But, yeah, you'll see this in competitive programming literature, I guess. But I'm looking for more specific. I'm looking at the Morris Traversal. I don't know if there's a way in order, ascending sorted order. I'm wondering if I need to perform, if it's possible, first off, to use a stack to perform the Inorder Traversal. I don't think so. That's what I think you can use a deck to perform the Inorder Traversal. What you would do is, I think all the left subtrees you'd push onto the left side of the deck, and then all the right subtrees you push on the right subtree of the deck. Or actually, you could do it like, I don't know, I guess you would, also, I guess what you would do is you would push everything on the left side to the left of this particular value in the deck. I don't know. I actually don't know. I don't have a good answer for how to perform the Inorder Traversal without doing it recursively. Even with a stack, it's challenging, because I guess you process. I think what you gotta do is you gotta push. You don't process any of the nodes on the stack until the node at the top of the stack is a leaf node. I think that's what you do. And then if it's not a leaf node, you're gonna push the left subtree. You basically have to emulate the call stack, so it would be like you push left subtrees onto the stack until there's no more to push on the stack, and that's when you would pop the stack, or not pop the, you would process that node that process the top of the stack. There wouldn't be any left or right nodes to push, and then you pop it, and then if there was a right node, you would actually push that onto the stack and process that subtree, which would be the same sort of routine, which would involve pushing the left side of the tree until you get to a leaf node. Yeah, so it's very similar, I guess. And you would, right before you, well, if you pop the stack, if you just pop the stack to get this value that you're looking at, then you would process it, you would push it onto the array, and then, into your array, you process the node, and then you would push the right subtree, which would enter the same routine again. Yeah, I don't know. It's like it's basically like putting this whole sequence into its own function, I guess. Yeah, you need to emulate the call stack with a regular stack. Excuse me, which is a challenging thing, because this would push, you keep pushing things onto the stack for processing until there's nothing left to push, and then you pop that part, right, when it's empty. Yeah, and you kind of queue up these other functions as part of this call stack, which is kind of weird. That I think that's the thing about the call stack that's kind of strange, is that you're actually queuing up other commands as part of the call stack, as part of the function. Yeah, so it's a little bit tricky to properly code that, I would say, overall. Like, in theory, you could emulate the call stack, but there's really a lot. You have to actually emulate like a whole function that you would call. It's very tricky. Doing fine. I'm glad. You don't mind me. I'm over here just pondering, sort of an optimal way to solve this problem, I guess. I already came up with some way to solve it. This isn't actually the correct way this isn't really the correct way to solve it, but one approach. But yeah, I think part of the issue is emulating the call stack can be pretty challenging. I think the thing to do would really to be you would write a subroutine that you would call, and then in the stack you would push that subroutine with parameters, I guess. I don't even know, actually. I'm not really sure how you would emulating the call stack. It's not something I do very often. It's a challenging thing. I do know, though, that you can do an Inorder Traversal with left node, right, left, right node. Yeah. an in-order, you can do a binary, you can do an in-order traversal, which would, using threading, iterative in order. Oh, here we go. Oh, I couldn't figure this out. Really? So if the node's not empty, push the node and then go to the left subtree. Otherwise, pop the node, process the node, and then push the right side. And you keep looping. No kidding. I thought maybe something like that would work. Yeah, alright, fair enough. I've actually looked at this in the past. I had a hard time like thinking of it again. Alright, let's try that. So we're gonna say while. So what did they say? They said, well, I should be able to figure it out. Let me try to figure it out for myself again. So while it's not empty, and let's do it this way. So we'll say, so we're gonna say tree node current is equal to root and current, right? So it's not equal to the null pointer, we'll say. What we're gonna do is, so if current is not equal to the null pointer, then we're going to process the left subtree. So we're going to push st.push current and set current to current left. Otherwise, this is kind of, I was thinking about something like this before, but the problem I ran into is like generalizing an approach like this. It's not a very generalized approach. It only really works for in-order traversal. It doesn't work for other kinds of traversals, like post-order, pre-order, in-order. I guess they all have their own special way of manipulating, of iteratively searching with the stack. I guess something like that. I don't know. Anyway, so you can say current equals now. Otherwise, if we are null, then we want to pop. I want to say current to SD top, SD pop, and then if we say, so stack's not empty, and actually I'm not sure about this one. What is the other condition they had? They had some other condition there. Or the node is not, while it's not empty, or the node is not empty. Okay, sure. Not and, but or. So I guess it's, oh, I see. I think I understand. They want to make sure they get this last node here. So it's not empty. We push and you go, okay, see, because the stack could be empty, but you could have a node you need to process. If it's not empty node, we push that and update to the left subtree. Otherwise, I take what's at the top of the node, and we pop. Our visit routine is going to be data.pushback current value and pointers.pushback. Same thing is going to be current, and then we're going to actually current updates itself to the right subtree. Something like this is what we need to do if we want to do this iteratively using a stack. I guess this is something I should have been able to figure out for myself too. In theory, I kind of already knew that, but I guess I forgot it. And yeah, I kind of stopped myself thinking it through as well. That's also true. But yeah, you could do this without using a function. Now, if you want to do this using threading, what you can do is there's called Morris Traversal. Now, there's actually a couple things here. First thing is we don't actually need to use this sorting at the end here. sorting and reassignment. This gives us a total O of n log n time, which is not really the optimal time. And it's also, there's a way to do this that's a little bit more efficient, which I think is just checking to see if the previous value, like as soon as we have the previous value is larger than the next value, then you have a problem. Now the question is, if that only happens once, that's those two values you gotta swap. If that happens twice though, that means two different values are in the wrong place. The question is, which one goes where? And you would swap there should be a larger value and a smaller value. I guess the question is when these are not in the right spot, what does it look like? Alright, let's see. And I guess, Melito, what I would ask is how are you doing otherwise? Like I recall that you mentioned that you were having some issues with your brother, and I was kind of curious, like, how are things going since then? So it looks like 3 is greater than 2, and 2 is greater than 1. But to fix this, you would need to put 1 with 3 and swap 1 and 3. Not swap 2 and 3 or 3 and, yeah, it's 1 and 3. So I guess the first element is should be too large, and the second element should be the second part. I guess it would be so that's hard to say, right? Because in this case, it's 3 2 and then 2 4, right? It's actually, yeah, it's only once that we see this. So if it's only the first time, then you swap those two elements. It only happens once they're right next to each other. But if they're not right next to each other, you swap the first one with the second one, I think. Yeah, I think that's the way to do it. So you do something like this. So to do this in linear time rather than n log n time. Actually, yeah, you do need to do. You can do 2 swaps, I think. So 2 gets swapped with 3, and then once you see 1 is less than 3, then you can swap the 1 with the 2. No, that won't work. No, it's got to be exactly 2 elements that get swapped. Yeah, it's a tricky thing. Okay. So we have, I guess, 4 values. Or just, yeah, I guess it would be. Yeah, okay. So which, and we're gonna say 4 and I equals 0. Yeah, I equals, well, it could just be tree node R in pointers. And you would say, no, actually should be done with an index, yeah. Should be done with an index. Yeah, fair enough. Okay. So say next or current is going to be pointers of I. We'll say if previous value is greater than current value, found a possible, found a pair. And we're going to say which dot pushback previous and which dot pushback current. And then I think we just keep going. Which this could just be updated over here. You can also, yeah, it's fine. I was thinking of using iterators here or something, but we're a piece. Okay, that's good. I'm glad to hear that. That's a positive thing. And how's church going? How's script? You know, how's like reading the Bible and praying and like have you talked to your pastor about what you're experiencing at home? Also. Alright, found a pair. So, yeah, each pair we're going to push, and we'll say, if only one pair was found, swap the data values. So we say if which dot size equals 2. Now we're going to say standard swap which of 0 value and which of 1 value if 2 pairs have been found. The pair value of the values must be swapped with the latter. Something like this. And then we don't need to use this. And so this will be linear time rather than presumably linear time rather, if it's correct, if it's rather than n log n time. Alright, nice. Interesting. What? A null pointer? What do you mean it's a null pointer? There's null pointers in here. How do we get null pointers in here? Is that even possible? I don't think so. Interesting. I don't think that's even possible. I don't know what happened, but I don't think that's possible. No, I haven't. You haven't spoken to your pastor about it, is what you're saying. Did you pray about it? Did you? I mean, you don't have to tell me that, but I don't know. I'm just curious how things are going. That's all. Me personally, I've been kind of struggling with some things. Like, oh, that's putting it lightly. A lot of things. We live in a broken, fallen world. Thank God. Thank God that we have Christ and we have redemption, and not just that we have redemption, but that we have forgiveness, That's kind of the prayer I've been praying a lot lately. Just thank God for saving me, an evil person, evil, wretched, wicked sinner, that I'm going to heaven after all of it. After all of it, I get to go to heaven. Praise God, thank God, just thank God. That's all I really could say about it. Now, my question is, how is previous? This is not a null pointer. Let's just debug code, I guess. Let me see. Presumably we won't need too much. We do live in this shambles. Yeah, it's true. So how did we end up with, excuse me, how did we end up with, this, what is going on? Let's print current. So it is initially something, but somehow how did we end up with a null pointer? How is that even possible? Oh, I'm sorry. Oh, duh. That's got it. I see the issue. Yeah, this has to do with I'm so dumb. I'm not dumb, I should say that. I make a lot of mistakes. I make a lot of mistakes. That's why. I know exactly what's happening. That's kind of subtle. Yeah, I see the issue. So, okay, well, I can move this out of the loop, but I can also... We can also use, like, pointers. Yeah, that's fine. We can just... Well, I guess you have to move one of these out of the loop. Yeah, fair enough. Fair enough. Something like this. It's not that subtle. Oh, I see. Alright. Well, we can just do that too, I guess. Fair enough. Oh. My mistake. Make a lot of mistakes. There we go. Alright, so it's wrong, but at least we're not crashing now. Why is this not correct though? Okay, my output. Oh, I didn't change them at all. Is that right? So, the previous and the current value, we could print those values. Find out what happened. Yeah, the fallen world, man. The fallen world. It's pretty astounding how broken it really is. So initially, oh, I see the problem. There are a few mistakes here. Okay, got it. probably has something. This probably has something to do with what's happening here. Oh, okay, it's correct now. All right. Now the question is, it's correct on this case. Now let's try some other test case to see what happens. I don't think this is right on other test cases, not necessarily. Oh, it is. Okay, perfect. All right. Yeah. So now we have something a little bit better. This will work on. So this we don't need to sort and reassign. So now what's valuable about this is that, and it still isn't fully correct, but now we can actually interleave what's going on this logic, and we can say with this logic, so we can say there's current is the root. We'll do current previous. Also could call it the root. And we're going to say when we process, we're not going to data push back. We're going to say current is then, or not current, but we'll call it like tree node x is equal to, well, it actually really is just current. So we would say if previous value is less than, or is greater than the current value, then we would, these we don't need anymore. And we can say which dot pushback first previous and second current. And then we don't need these two anymore. Something like this should do the trick. Also, previous becomes the last node that we processed. So yeah, so then we say previous equals current. We could try something like this. If I can get the syntax correct. I think this is correct now too. Let's find out. Wrong. Oof, okay, fair enough. Now why might that be the case? So the logic that I had before was pretty good, but something wrong here. I think because, well, when you process, and you would normally push back into the data, so what do we got? 239, and we expected 529, 539. So 5 would be the first, and the second is 9. Now where did I get the, oh, I see, okay. Actually, I would see 5 and 3 and 9 in this one. Also, forgot that I have my my email still up here. I have a bad habit of leaving that on when I live stream here. So that's really interesting. So previous is greater than current. That happens once here. And that happens a second time here. Now what's interesting about that is we would push both of these onto the stack. Now somehow 2 got swapped, but I would expect actually 529. Oh, I see. Well, what's interesting about that is we didn't really print the data that would happen, that would have come out here. Oh, I see the problem. Well, no, not exactly. I think what's happening is that this really should be the null pointer. I think that's the problem. I think that's the issue. I think that's what happened. Yeah. I'll explain what's going on with that in a moment. Yeah, it's a tricky thing, gotta be careful. Yeah. I think I know what happened. Perfect, okay. So the issue is that I had put something in previous, and the problem with that is that once you've already traversed the array, all of these pointers are in the right sequence, and so you can set the previous to just start at the beginning. It doesn't really matter what it's pointing to. But since we haven't already sort of like sequenced the array, I guess, or sequenced the tree, that initial pointer, if it's just pointing to the root, then whatever we have, the first thing we compare it to, it'll actually make that comparison. And then what can happen is that comparison could actually pass this check, and then that gets pushed into array as if we found one of those pairs, but it's a nonsensical pair because it shouldn't even happen, that comparison, because we're comparing things that are out of order to each other. So you just make sure that there is a previous node to compare it to, and then you're fine. So yeah, so this is how you can actually make this a little more concise, and you don't need as much memory. But there's a problem with this too, and I'll explain that in a moment. The problem with this is that even though this works, and it's relatively efficient and it's simple, the issue is that this still uses stack to perform the Inorder Traversal. As part of the question, they say, hey, you can do this with linear space. Is there a way to do it with constant space? The constant space solution is the same one as this one, except you use threading, and you do Inorder tree traversal with threading. So we're going to do that now. I've done this many times in the past, but so what is this? Single threaded. Each node is threaded towards either the Inorder predecessor or successor. Double threaded. There's 1, 2. So I guess in Python. So what I want to do is thread and then perform the Inorder traversal. However, the traversing a threaded binary tree without using recursion, any such method must use iteration. All steps must be done in a loop to visit all the nodes in the tree. Actually, no, we'll just write Morse traversal again. I've studied Morse traversal a few times, and I never remember these things because they're just things I usually just look up. But yeah, I guess to just remember the Inorder traversal, you would, if the stack is empty or you have something in your pointer, right? You're not pointing the null pointer, then you're going to. It's a while loop. You're going to say if it's not a null pointer, then we push onto the stack and update to the left subtree. So we go all the way down the left subtree first. Otherwise, if we are a null pointer, then we're going to, and the stack is, then we know the stack is not empty in our while loop. So we could pop the stack, and then we could take what's at the top of the stack, pop the stack, and then process that element, and then push the right subtree, and then repeat basically on the right subtree. And this structure, for whatever reason, this particular while loop happens to emulate the Inorder Traversal. That's pretty simple to remember. Moore's Inorder Traversal using threading is a little more involved. One traversal at a time, more prone to errors. Both the children are not present, both values of nodes point to their ancestors. Implementation of Inorder Traversal uses threading. Yeah. Can we... Well, I guess it's the same article then. Yeah, so let's perform the Inorder Traversal, the Moore's Traversal. How are we doing on time also is the question. Yeah, about an hour. I need to go to bed soon, actually. I wasted a lot of time today, I'll be honest. I mean, not honest, but I shouldn't say that. That's a bad expression. That's not something to repeat. Not something I should say. I'll be to confess. I will confess that I wasted time today doing all kinds of things that probably weren't the most productive. Threads are reference to the predecessors and successors of the node according to an Inorder Traversal. So how do we thread the tree? Inorder Traversal. So if the current node has left child, which is not in the visited list, I go to step 2, otherwise go to step 3. Traversing a threaded binary tree that recurs in any such method must instead use iteration. That is, all steps must be done in a loop in order to visit all the nodes in the tree. By definition, visit while we're looking for Moore's Traversal, though, specifically. And we want to use that. Obviously, I did not invent this algorithm, so it's not something that I know very well. Oops. Didn't mean to do that. Okay. I think I memorized Moore's Traversal, one version of it. Okay, so this is Moore's Traversal, alright. So what do we do? The node is not, so I think we thread it and traverse at the same time, something like that. So there's no explanation of this. If node is in the node tree root, return none. Or node is the root, return none. What? What is going on here? Parent. Otherwise x equals node, y equals node, while true is thread. D equals y dot root. What is this routine? I don't understand. I'm so confused. node has a left child which is not in the visited list. Go to step 2, otherwise step 3. Put that left child on the list of visited nodes and make it the current node. Visit the node if the node has a right child, then go to step 4, let's go to step 5. Make the right child the current node, go to step 6 if there is a thread node, and then make it the current node. If all nodes have been printed, then end, else go to step 1. You can avoid the visit list of visited nodes by actually making like a circle with your traversal. Basically, you would take the right node, and if so yeah, you can make like a modified. I'm gonna list it down for this. If I remember it correctly, you can make a modified traversal that doesn't have a visited set. Hold on 1 second. Give me just 1 moment here. This is something to learn for me. So the visited set, you don't need a visited set, because what you can do is you can take the right node if it exists, and then you can take all the left nodes excuse me, until I think you can traverse the left subtrees until you get to their starting point. And if you do reach your starting point, that means, what does that mean? That means it's a valid ancestor. Yeah, you can figure out whether or not you're an ancestor or not. I think it's something like that. I forget exactly how this works. It's like you would, instead of pushing things onto a stack, you would traverse all the way to the bottom left, and then process that node, and then move to the right to get the ancestor. Excuse me. You can check if that's an ancestor by, again, moving all the way to the left to see if you end up in a loop, right? If the node that you came from turns up. If it is, that means you're in a valid ancestor. Then you would process that ancestor, and then you would operate on the right subtree again, and that might take you either up the ancestor tree, or it would put you back into a. And also, by the way, once you jump up that ancestor, up the tree, you unthread, so you dethread while you go. You do the same thing again. If on the right side, if you perform that check, then you go all the way to the left, and you don't see the node that you started with, so it's not an ancestor. That means you're in a new tree, and you're already in the right position to begin. So you would process that leftmost node as well, and you would continue from there. Yeah, to actually thread the tree, you do a similar thing where you have excuse me. You take the left subtree's rightmost node, and you thread that to that particular node. So you would perform an Inorder Traversal, more or less. So for each node, you take the left subtree's rightmost node, and you thread that. And then once you've returned to the, once you've threaded that node, I think you would do that on the left subtree. You'd perform that on every left node. So you thread all the way down to the left. And then the tricky thing with that, though, is what about the right subtrees? Yeah, so what you would do is you would continue iterating on the right sub. So first you would process the left subtree and then continue on the right subtree. I think to do that, you would tricky thing about this is that you need to start the threading. I guess you could do sort of the left half of the tree first and then do the right half of the tree. But you kind of need to do this in such a way where you always get the right subtrees. Just thinking here, maybe that's what the parent routine's supposed to do. That's how I think that's actually what that parent routine's supposed to do, is to actually thread the binary tree. So you can run one routine to thread the binary tree, another routine to iterate over the binary tree. The first routine to thread the binary tree in the first place, you would you would first perform on the left node, right? So that would be the rightmost subtree, or the rightmost node in the left subtree gets a right node back upwards towards the parent, and then we can then return to update the parent to the left subtree's node, right? And then the problem with traversing down the left side is that we then need to come back upwards. I guess what we would do is we keep performing this routine until there is no left subtree at all, and then we just immediately set the right value up to this parent node, and then we take a right again. So that would perform the right subtree there. Two rights, I guess. So we would return to the parent if there is no. So if we reach a leaf and there is no left subtree, I guess let's say there is no left subtree, then we will update to the right side, which would become, we assume, would be a parent, and then we update our parent again to the right side. So we could just make two right jumps, and then we process that subtree, and then somewhere along the line we jump back up to the next parent, process that right subtree. Yeah, I see. Yeah, that'd be fine. That works. So we would traverse down the left side, and then to process the right subtrees, we would just jump, make two right jumps using the threads to come back, and then you just keep operating that way. That works. So you can thread the subtree using that routine. You do, if there is a left subtree, if it exists, then take the rightmost node of that subtree and thread that back to your current parent node. And then once you finish that, you would update the parent node to the left subtree. And then if there is no left subtree to at all, then you're going to update your node to where you currently are, the current parent or the current node, and you're going to make 2 writes. If there's no left subtree, so you update the parent node to left subtree. So if there is no left subtree, then you make 2 writes on your parent node, and then continue. If it exists, at the very end, you have to be careful because there might not be 2 writes to make, or even 1 write to make. If there's no writes at all, which with the threaded tree, there will always be a write that you can move to. You actually need to be careful because the writes that you make could actually be to other parent values. So what you need to do is just check that you haven't already visited this node, and the way to do that is you can run a loop. So what you do is you would update a variable. So when you make that write, you update it. You have a variable that's the head of the left subtree, and you can just iterate. Really, it would be to know that you jump to a parent. It would be that. Well, I guess I'm actually not entirely sure. I want to say something like you have to handle that jumping to the right properly, where you need to make sure that you jump to some other. You need to make the distinction between jumping to another parent node you've already visited, that you've already threaded, or a fresh new node. And I guess the way you check that is you would just iterate towards the left to see if you reach a node you've already visited. Yeah, you can keep the previous parent. I think works like it's an ancestor, so something like that. I'm actually not sure exactly how to do that. So if you're, because part of the problem is that like let's say you have a very large left subtree, a very large right subtree, and you're on the rightmost node of the left subtree, and you jump all the way to the root node. Excuse me. The tricky thing about that is, how do you check that? How do you determine? Yeah, I got it. Okay. Here's the thing. The right nodes, they could be new subtrees, or they could be the parent, or you could just be following another thread. So what you want to do is you make 1 write, and you set some variable to that, and then if there is another write that you can make, if we're not empty, right? So if we're not empty, we set a variable to that. Then we try to make the next write. So the next write, it could be that the left subtree of our next write is what we just checked, which means that we're going up the left side. We're going just up a bunch of threads that are just one after another. In that case, we're not actually at a new subtree, and we want to actually perform a while loop there and keep going up until we actually find something new. Once you find something new, then you can just continue. You can throw away that variable that you were using to check. Excuse me. I think that's fine. I think that works okay. I think that works okay. Yeah, so you'd make 2 writes, and then you might have to make a while loop to make sure that these 2 writes, like you need to make multiple writes, right moves in a while loop, such that you actually end up at a new right subtree that you haven't processed yet. So that's how you can thread the binary tree, and then the iteration through the threaded tree is almost exactly the same. except you just remove the threads this time around. Yeah, I think that's it. So that's how you can thread and iteratively traverse a binary tree. I think it's something I need to spend the time to practice. I don't really want to do that now, but in theory, it can be done. So, alright, so we're at like an hour and 20 minutes now. It's quite a bit of time that we spent thinking about how we can do this in a way that saves memory. Yeah, you can thread the tree, and then you can traverse the threaded tree and unthread it while threading it. Well, yeah, thread the tree and then traverse the tree again, but unthread it the second time and also process each of the nodes as you visit them. The idea would be you kind of do a similar thing as this, except you go left all the way down, process that node, and then take the right node, process that node, take the right node again, process that node, and then left all the way down again. Excuse me. Left, process that, left all the way down, process that node. You go up to the parent node, it would be, process that node, right? You check if it's the parent by well, actually, I guess the right node, you always would just process it. And then, the tricky thing is you need to know whether or not that's a parent node or like the end of a right subtree. I'm actually not sure how you would iterate through it at the end. Now that I'm thinking about it, I think it is actually the same thing, same algorithm that you perform with threading the tree. So you go all the way down to the left and process that node, then make one right, process that node, make another right, and if that's another parent, you would process it again, and you keep iterating until you get to a new right subtree. Once you get to a new right subtree, then you go to the top again. You don't process that node yet. Yeah, you go all the way down the left, and each time when you jump upwards to a parent node, then you would that's a thread. Every time you take a thread upwards, then you would remove that thread and process the node, and then so the leftmost node you'd process, and then you would follow the threads until you get to a right subtree that's new, removing the threads, and then you would move all the way down the left. So yeah, it's the same. It's the same. The threading algorithm is the same as the traversal algorithm. Both of them are linear in the number of nodes, and both of them would give you a way to process the Inorder Traversal. That would give you no extra space, and it's pretty involved. But we're not gonna write that solution just because it's, like I said, it's kind of involved. It's not too bad, I guess. It would be a good exercise, but I'm not gonna do that now. Maybe later. Maybe tomorrow I might take a look at it. Not tomorrow. I might do it. I might take a look at it. Not tomorrow, but I guess maybe Wednesday. All right, I'm gonna go now though. I think that's enough for me. That's pretty in depth. Yeah, at some point I think I'll probably have that memorized, how to perform the threading and the Inorder Traversal and removing the threads. I think I'll do that in the future. Verify a binary search tree is indeed a binary search tree, I think, is actually to check if the Inorder Traversal is monotonically increasing. I think that's another way of doing that, by the way, which is a pretty nifty approach to this problem, to verifying a binary search tree. Yeah, you could actually perform an Inorder Traversal or a Morse traversal. Yeah, you could do an in-order Morse traversal. That's iterative, it's not recursive. And just check that's every node is from the previous node to the current node, that you're monotonically increasing. I hadn't thought about that. I hadn't thought to do that with a binary search tree. That's a really interesting way of verifying that a binary search tree is a binary search tree. Yeah. So let me, that's a really clever way of answering that question also. Let me go, I think I'm gonna go. You know what we'll do at some point in the future, I'll revisit the verifying a binary search tree, and we'll try to use a threaded tree with a Morse traversal and try to implement that. That way we have it memorized, and I can always just pull that out during an interview. That would be really interesting. Okay, so thank you again for watching. I'll talk to you all soon. Have a good rest of your night. I'm going to go to sleep. But yeah, it was good seeing you, Melito. I appreciate it. Appreciate you coming by and saying hello. What I want to say, I don't have much else to say other than, like, thank you all for watching. I'll talk to you soon. Have a good rest of your day or night. And yeah, I have an on-site tomorrow, so that's gonna be interesting. What do I want to say? I don't know what else I want to say here. Yeah, have a good night. There's like a bunch of problems I want to work on that I want to go through and stream. There's like a whole bunch of things to look at. But yeah, alright, I'm gonna go.